Okay, good afternoon. So let's start this class with the question, do you have questions, not me? Yeah. Like regarding the quiz next Monday? So next week, on Monday, you should try to be here probably 5 minutes before 1 o'clock. Simply because for 60 people it does take quite a while to hand out the quiz, etc. And we will start sharply at 1, we will stop sharply at 2:30. Okay? There's another class scheduled right after us, so we cannot have any additional time. There's no way for that. Okay? Please be aware of that. So whatever you do, don't come late. From the topic point of view, is everything clear, like what will be covered in this quiz? And do you have any questions? Yeah? There are a lot of what? So there are 2 or 3 things. One is Amdahl's law. One is the CPU performance equation, which is definitely also required for the quiz. I think they have a somewhat more detailed discussion of geometric means versus arithmetic means in the spec MPI chapter, or spec chapter, sorry. We did discuss it very briefly, but I won't ask any specifics about that. Cost and power we did not discuss. Okay, so you should read it. As a good computer scientist, you should be aware roughly what this means. What they really do there is basically give you a formula on how expensive a chip is depending on the size. And then they give you some examples on how, depending on the size of a chip, how expensive something gets. I think it's a useless exercise, to be very honest. Yeah. Other questions? So you are allowed to have 3 sheets of paper, and you are allowed to write on both sides of it, but only handwritten. So this adds up to overall 6 pages of handwritten notes, which you can bring with you. This should be more than enough usually. Yeah. I would not know what to put on that that many pages right now, but yeah. So I can't tell you precisely how many there will be. I can tell you that for last year, for the first quiz, there were all in all 5 exercises. Some of them had basically parts A, B, and C, but not all of them. So those of you who did not have yet a class with me, additionally to the type of things, so what we did in the last class, in the exercise, what I typically also ask is things like, explain briefly how correlated branch predictors work. Okay? And then you have to be able to write in your own words, in 3 to 5 sentences, an explanation on what the idea behind the concept, how it works. Okay? So I do ask a couple of those high-level understanding questions, and I really, really, really would love to see they're your own language and not what I wrote on the slides. I know what I wrote there. I want to know whether you understood it, not just that you can copy the location from the slide onto the quiz. Okay? So that's very important, and I think that's usually, for people who attend my class the first time, that's the biggest hurdle for what they are not prepared. I usually do not have multiple choice questions. I don't like them. But there might be one, just for fun. Yeah. The reason I don't like multiple choice questions is because you have 2 alternatives. One is you basically give points if the student has the right answer. Now you might make it slightly more difficult by having more than one correct answer, in which case the students have to detect it. Now unless you introduce, however, also the idea that a wrong answer gives negative points, a student doesn't have anything to lose by adding some ticks. Yeah. So that's not the point. If you add, however, negative points for a wrong answer, it's very easy for a student to get very low. Yeah, so I witnessed that a couple of times, and it's very easy to end up suddenly in the 40% range, where you would not really belong in a knowledge-based quiz. So that's why I usually try to exclude those type of questions. Yeah. I think I mentioned that you might need a calculator. Yeah. Anything else? So yeah, I have this afternoon again office hours, but also please feel free if you have questions to contact me tomorrow. Friday I'm out of office in the afternoon, but if you cannot make it by tomorrow and you have questions, just write me an email and I'll answer. Okay? Just if you have a long list of questions, an email is probably not the right way to go, because yeah, I don't want to spend an hour answering your questions. Yeah. I don't mind doing that if there's no other way, but if you can come and stop by my office to answer questions, it's simply easier. Okay. Anything else? So we are still fighting with VNet, how to upload those files properly. So as soon, I'm still doing the recording, and as soon as I figure that out, what's wrong, the classes will be made available. Yeah. Did I mention that I'm gone on October 31st? Yeah, so I would really love to try there to have the class only uploaded such that we don't have to reschedule it. And I would like to have afterwards your feedback on whether this works, whether it doesn't work, or what's the problem, okay? Or how to improve it maybe even. Yeah. I know many of my colleagues right now teach mostly online classes, and I would really like to know after this one experiment, maybe October 31st, whether you think that's realistically an option, or is there any benefit of having the instructor really sitting here in the front and jumping around, or because if not, well, then that's the teaching form of the future, yeah. Okay, so let's continue topic-wise where we stopped, not on Monday, but, well, actually Monday before we started the exercises. So we've discussed in details now two things over the last couple of lectures. One was how to introduce dynamic scheduling. I would like to emphasize dynamic scheduling at this point really means on the hardware level. So Tomasolo's algorithm, scoreboarding, are really implemented on the hardware level typically. They take as an input what the compiler generated as a sequence of instructions, and they try to optimize the resource usage of the processor by executing as many instructions as they can, taking, looking at the same time at data dependencies, looking at what's the impact of out-of-order execution with respect to write after read, read after write, and write after write hazards. Yeah, we did discuss how Tomasolo handles that. We did discuss how scoreboarding handles that. We saw that one of the major drawbacks of this approach so far is that as soon as you have a branch in the sequence of instructions, you basically have to stall your entire system in order to know where you have to continue, whether the branch will be taken or whether the branch will not be taken. As a consequence, we discussed various techniques on how to predict the outcome of branches. We saw there are some static approaches which basically can be introduced on a compiler level or on the hardware, both actually. Yeah, you can do predictions like I always assume a branch will be taken, or I always assume a branch will not be taken. This does not reflect any behavior of the code, and any decision which you make can be arbitrarily right or wrong for the entire program. So if you make a decision, I treat all branches as they will be taken, well, you could be in 100% of the cases wrong. So what you really want to do is what you really want to see what your program really does, how the branches behave, and learn from that. And that's what we try to do with the dynamic branch prediction algorithms, and typically are implemented in the CPU, where, well, the main idea is if you execute the same branch instruction over and over again, you might want to learn and basically benefit from that. And the second idea, the second main idea which we discussed was that the outcome of a branch might actually be influenced by the previous branches in the code. And you try to detect their pattern in the spaghetti. Yeah, like if the last branch has always been taken, then my branch will typically not be taken, and so on. So there were several techniques. We saw how to correlate the length of the history to the outcome of your branch prediction, namely whether you are looking at one instance back in time or two instances or n instances. This gives you basically the 1 or 2 or n bit predictors. We saw or discussed how to adjust the number of branches which you are looking back in time, and not in time, in the sequence of instructions, like are you looking at the last branch before the current branch or the last 2 or the last n branches, and do you monitor their behavior? And we basically discussed there 2 different algorithms. One was correlated branch predictors and briefly tournament predictors. Yeah. Now at that point, however, what we only did was really to predict how a branch will be taken. This does not yet have any consequence for Thomas Hulu or for whatever. Yeah. And that's what we are doing today. We are extending this idea that we can, or we are using the idea that we can predict the outcome of a branch in order to improve the performance of our out-of-order execution engine. Yeah? And that's typically called hardware-based speculation, or speculative execution. So, as I mentioned, branch prediction, we hope to reduce the direct stalls of the pipeline due to branches. And as I mentioned, as long as we are only looking at the branch prediction itself, it doesn't really solve yet our problem, because we do not have any method to execute and to undo instructions in case of our prediction was being wrong. So hardware-based speculation or speculative execution is really the next logical step if you're talking about branch prediction. So we extend the concept of dynamic scheduling to not only predict the outcome of the branch, but also to execute the following instructions. And we will introduce now the concept of how to undo instructions. So the thing which is really being introduced in Thomas Hulu's algorithm in order to support speculative execution is what is called a reorder buffer. So basically at the write back step, we are not writing back into the register result, into the register file, but we are writing back into what is called a reorder buffer. And in the reorder buffer, we are actually ensuring that the order in which we commit the instructions from that reorder buffer into the register file again is in order. Okay, so we will have now suddenly in order issuing of instructions, out of order execution, and in order committing of instructions. So these are basically, this is basically one additional step after the write result. We will see in a minute on an example how this really works. Yeah. The reorder buffer itself, you can think of that as additional reservation stations. As soon as a data item is available in the write back stage, you are basically writing the according content into the reorder buffer, and you can therefore free the reservation station itself. Other units still can use the data, or other reservation stations still can use the data after the write back step. So the reorder buffer really only is like an additional temporal buffer. Now in case, the big advantage is if in case it turns out that your branch prediction was wrong, what you can do is you can flush now the reorder buffer. No register has been touched yet, and you are capable of simply re-execute the right sequence of instructions with the original data input. Okay? Input data. So what we need is basically 4 fields for the reorder buffer. 4? Yeah. An instruction type. What type of instruction this is being? The destination register number. Okay. We need to be able to store the value of the according operation in the reorder buffer, and we need a flag to store whether the according instruction has been executed or not. If you have an instruction like add R1, R2, R3, the value is the result of R2 plus R3. So the value of the operand of the data item which will be written back to the result register.
So you're not keep track of the instruction where it is in the sequence. How do you know what order it is in?
Good question. Let's look at the example. To be very honest, I have to think a little. But I think you have the sequence of instructions still also in there, based on the based on the instruction type itself. Yeah. Okay, so the 4 steps of execution now in our modified Tomasolo script is with issue an instruction, basically get the next instruction from the instruction queue, and we basically have to check now if a reservation station is empty. By the way, I can answer your question right now. I just realized the answer. You can issue an instruction if a reservation station is empty and a reorder buffer is available, because on the issue step you are adding the instruction into the reorder buffer as well. Okay? So they're added in order. Yes, because we issue in order, the order in the reorder buffer is the same. Okay? We execute the instruction as up to now, as soon as the operands are available. One of the modifications is that in the execute step for a store operation, you cannot really execute that operation. Why? Because you do not know whether the input operands were really valid or whether the instruction itself is valid. Yeah, it might be that you've chosen a speculative path, and this will be invalidated at one point in time. And basically, before you write back into main memory, you want to make sure that the branch or the path which you've taken is really the correct one, not a speculative one. The write back stage is still similar, so you write back your result to the common data bus, and this updates reservation stations which need the entry, and reorder buffers as well. So that's why a reorder buffer from the hardware perspective is really something very similar like a reservation station. The register file itself, as I mentioned, is not modified at this point. The commit stage, well, we have to distinguish now a couple of different scenarios. For the normal execution, and by normal I would claim that the speculation was correct, what would happen is your instruction basically has to reach the head of the queue before you can commit it. Once you the head of the queue of the reorder buffer, you can update the register, the result register, and remove the entry from the reorder buffer. For store operations, as soon as you reach the head of the queue, you can update the memory location and remove the operation from the reorder buffer. Now, if your prediction was not correct, so that's the non-normal case, then you are basically able to simply flush the reorder buffer, flush reservation stations, and restart the execution of the instructions at the right spot. Yeah. So let's go through the very same example which we had previously. The same assumptions for all of regarding the number of reservation stations available. I prefer red. And the same number of cycles for each of those units, and let's see where the difference is. Okay. Time step 1. Issue the first load operation. Basically means add the according fields into load 1 unit. Okay. One of the differences now, you do not store the in the destination field. You do not store anymore which register will hold the final result, but which reorder buffer number holds the will write the final result. Similarly, for the register result status, we do not really store which reservation station will produce the according result, but which reorder buffer will in the end write the according register file. Okay, so we just have to remember which reorder buffer will write it and whether this register is right now busy, which means there's an operation which will overwrite the according entry. You have now suddenly, however, also a fourth table, which unfortunately did not fit on the previous slide, which is the reorder buffer itself. And basically you add your instruction, you set a busy flag. You want to probably remember, did we have the state? No, we just had in the requirement list that we remember whether the execution has started. So here we are right now simply storing what state this instruction is in. That's not really required, but it helps us right now in the example. What's the destination register and the value in case it is available, yeah, which is not yet. Second iteration, the load 1 unit does the effective address calculation. We can issue the second load operation, which will write the result into the second reorder buffer. Yeah, set the according register status flags accordingly to point to the right reorder buffer. Yeah, and add the instruction into the reorder buffer as well. Yeah, so we updated here also the state of this, the first instruction from issue to execute. Time step 3, the first load starts the execution, so it reads the memory address. The second load does the effective address calculation, and the mult is issued, which now has references that one of the operands is not available. So instead of now storing which functional unit will produce the according result, we remember which reorder buffer will contain the according result. Yeah. Update, similarly the same register result status, add instruction to the reorder buffer. Next step, the first load basically finished the first load finished the memory access operation and writes back the result into the reorder buffer. So this unit is gone. The register, it was register F6, however still contains the according fields, right? Because the result has not been committed back to the register itself. That's one step later. The second load executes. The multiplication here has been stalled because the according, we are waiting on the reorder buffer number 2, which would be in that instruction the register F2, but that's not yet available. We have to wait for the second load to finish, but we can issue the next operation, which is the according sub. Yeah. So please note, here the write back stage, we basically transfer the content already to the right into the right field for the subtraction. Okay, so this data is available with a write back stage, with a write result stage as well. We do not have to wait until the commit. Now what's that? I'm pretty sure I had originally the reorder buffer in here, but it doesn't change yet anything. So time step 5, we can now commit the first load operation. The second load operation writes the result, update all the fields. So why can we commit? Because we are the head of the reorder buffer. Yeah, we are the first instruction. We have the according value, so we can commit. For the second instruction, you see we have the content already stored in the according value field. Yeah, but we will only be able to commit at the next time step. Yeah, in the sequence, and this is happening now in time step 6, where the so I'm not sure we should go over all of those things, but I want to point out one more thing in a minute. So time step 6, we issue simply the next operation. The multiply starts. Time step 7. So this is now getting interesting. So the subtraction in the add one unit has now finished execution. So in the next step, he will do the write back. Okay. So the add one unit wrote back the result. I would like to point it out. The next instruction, so the previous instruction in the queue is the multiplication, which is, however, still in the only executing step 3 out of 10 of the execute part itself. And because of that, you have here now the content of the result of the according operation. I just called it x. But in time step 8, you will not be able to commit. We have to wait to commit. Why? Because we are not at the head of the reorder buffer. So this operation will not be able to commit until the multiply, which is ahead of it, did not commit. Okay? The same, so time step 11, what happens in time step 11? Oh, okay. The add finished. So we are also here in the right result, the last instruction. But similarly to what we had previously, this instruction is also not able to commit its content. This one is still waiting, yeah, because all previous instructions have to finish. Finally, time step 16. The multiply operation here writes the result. So we know that in the next cycle 17, in cycle 17, he is now able to commit, right? And in the next cycle, we will be able to commit this instruction, 18. Okay, so we have cycle 18, we committed it. Now this is a division which takes 40 cycles. And because of that, I did not detail all of those cycles. But we can point out that basically the 40 cycles are over in cycle 57, when the division writes the result. 58, the division can commit, and so in cycle 59, you can commit the add operation, the last instruction in that queue as well. So the general idea, once again, I think it's fairly simple. Store the results in an intermediary buffer, and wait until it's really your turn to commit. So we have in-order issuing of instructions, out-of-order execution, and in-order committing. And because of that, if you would have a branch operation within your queue, well, even if you have a prediction and you go and execute a sequence of instructions speculatively, in case the branch turns out not to be correct, well, none of the instructions which have been issued after the branch operation have touched any register. And therefore, in case it turns out it's wrong, you can just simply continue from the other spot of the branch instruction. Yeah? So it's fairly easy now to implement in hardware. Okay?
So, in reality, with the order buffer list, as one becomes unbusy, it will move up.
Yes. It's in reality, it's a queue. Yeah. Just for the visualization purposes, I didn't want to shift the operations up. Questions, or is the idea clear? Easy? Okay. Then we can move on to the next part. That's also actually a fairly big topic. So far we had one major simplification in our assumptions, namely that we can only issue one instruction at a time. Right? Now, why is that? Well, there's actually no really good reason for that, except that it's what processors did originally. So basically, if you could issue more than one instruction at a time, what you could solve is you could really reduce your ideal CPI. So far, we basically try to remove all sources for stalls, like branch stalls or pipeline hazards or whatever. But the ideal CPI, which you have to use in your speedup calculation, well, we didn't really touch it. Now, if you could issue more than one instruction at a time, what you could really achieve, assuming an ideal situation, is that you, on average, would need less than one cycle for an instruction to finish. If you can issue 2 instructions at a time, you have enough functional units. Each of them works in a perfectly pipeline manner. In theory, you would have an average suddenly that an instruction needs half a cycle for finishing the operation, right? So your ideal CPI is now, instead of 1, suddenly 1/2. So processors actually do really do that. There are 2 major flavors on how this is being done. One is what your Pentium and all major processors really support, and this is called a superscalar architecture. The other one is actually a fairly old concept called very long instruction word. This is used as an example by the Intel Itanium processor. This was actually one of the revolutionary things which Intel and HP originally wanted to do with the Itanium. They said, well, speculative execution and out-of-order execution increase the complexity of the hardware so strongly, they use so much power and so many transistors, can't we really do something different? And they basically digged out this fairly old concept of very long instruction words where you are issuing, or the compiler issues not a single instruction, but it generates and marks which of the instructions can be executed at once. So you are moving burden here. Well, let me do it. In this concept, you are moving the burden from the hardware to the compiler. The compiler basically has to tell you which of the instructions can be executed in parallel. What it will typically try to do is it will typically try to create so-called issue packets of 4 to 8 instructions, which it marks as one issue packet, and where it says from the pure data dependence analysis, these instructions can be executed in parallel. Okay? So just a little overview of what is out there and what isn't. So you have, as an example, the old Sun processors, UltraSpark 2 and 3, which were really superscalar architectures because they could issue dynamically more than one instruction, but they were really, they really had static schedulers. So they did not use dynamic scheduling, out-of-order execution, respectively just very limited, right? Basically what the compiler could tell, what the compiler could reorganize here. But one of the things we will talk about that, by the way, as well, is if you issue multiple instructions at once, what you are, of course, increasing is, so basically you would also need more functional units in order to be able to execute more instructions at once. And you are also increasing what is called register pressure, because you would need more registers to be available in order for more instructions to finish on time. Okay? So therefore, hazard detection between different instructions, that's one of the major questions. Who is doing that? So the Sun processors did that in hardware. The IBM Power 2 processor was also superscalar architecture with so this, okay, let's go back. So the Sun processor basically had in-order execution. This one here has limited out-of-order execution. Yeah. The next step is basically the Pentium line and the new IBM processors, which offer out-of-order execution and speculative execution, right? Which they didn't do. You have then the very long instruction words architectures. Who remembers the Intel i860? So this was a processor beginning of the 90s, which Intel had. It was really a RISC processor at the time, in which they still propagated the CISC processor, and it was used in some of their parallel architectures, like the Intel Paragon. Yeah, they didn't really follow up on that line. Some of the techniques have been merged into the Pentium line later on, but they did have RISC technology already at that time really available. So here you really have static scheduling, so no out-of-order execution, no speculative execution on the hardware. So in theory, your chip can be significantly simpler, right? An extended concept of this very long instruction word is what is called epic architecture used by the Intel Itanium, where the scheduling is mostly static, but in the end they ended up reintroducing some of the dynamic execution things which we discussed, again, for performance reasons, because the first generation of the Intel Itanium, well, it turned out that for many applications it was that slow that people simply didn't want to buy and use it, and it was actually a fairly expensive processor. So, let's go back to talk about superscalar architectures briefly. So, a superscalar architecture doesn't necessarily issue a single instruction at once, but typically also does not have a fixed number of instructions which it has to execute. So it really depends on the processor as well as on the compiler technology. Yeah, I mean, you see what's on the slide. I don't really have to add anything on to that. So basically what you should remember here, we're talking right now about the issue step. The issue step is in order, so you do not have out of order issuing of instructions. Having a, what I really would like to point to is two things. So basically at the issue step you have to check for structural hazards between the instructions which shall be issued. I mean, two instructions within the same issue packet could actually cause suddenly a structural hazard which the compiler did not see or could not see, right? The compiler does not necessarily have the knowledge of when other instructions have finished and therefore when a functional unit is available again. So the instruction fetch unit examines each instruction in the issue packet in order. If an instruction causes a structural hazard or a data hazard, it will not be issued. Checking of structural and data hazards are fairly expensive operations. So because of that, what is really happening is that that issuing of instructions is really implemented in a pipeline manner. So you have two separate stages, one checking for hazards within the issue packet and one for structural hazards. Probably you can now slowly start to imagine why on an Intel, not Itanium, on an Intel Pentium, a pipeline had in the end something like 24 stages. Well, if even the issue step has to be implemented in a pipeline manner in order to reduce the clock cycle time, you end up simply with a very, very large number of stages, right? So did we actually ever discuss what's the drawback of a very long pipeline? No? So what is the drawback of a very long pipeline? Right? But if you go even one step back, well, a pipeline has something like what is called a startup time. So assuming your pipeline is empty, until you get the first result out, it will take as many cycles as pipeline stages what you have. Okay? So if your pipeline is 24 stages and you only have, let's say, one add operation or one floating point add operation, your code else is mostly integer operations, it will take for 24 cycles until this floating point add operation has finished. Right? The advantage of pipelining only comes up if you have many operations utilizing the same unit, and you can execute them without stalls. But if you have only few instructions which would utilize a particular unit, these individual instructions will take a very large number of times or cycles to execute. So the basic question is now, okay, So let's assume I have a pipeline of k stages. How many instructions does it take until I reach at least half of the maximum performance of the pipeline? Did we do this calculation in parallel computing? No? I seriously don't remember. Yeah. One final remark, it's the last slide, I forgot that I still have that. So we do not, I'm not sure whether this edition, the fourth edition of the book, handles in details how to extend Tomasulo's algorithm to multiple issues. I think it's straightforward, and I don't want to go through another 40 slides showing how this works, so let's just skip it, okay? It's really not difficult, and it really gives us any new deep inside knowledge. I think the extensions are straightforward. Let's talk about very large instruction processors in a minute. Okay. So some matrix on pipelining. Actually, let's go one step back. So as you can see, that's from another class. So what let's have a look at a very simple code, something like a loop in which we add up two vectors. Okay. We assume now that we have a clock cycle time of tc in this example, that we have a pipeline of m stages. The length of our vector is n. Okay, just to keep it confusing. The startup time of your pipelines, that's the time in which it takes to produce the first result of the according unit, is equal to the number of stages of the pipeline. So it should actually be lower letter m, not capital M. Okay. And one of the metrics for pipelines in order to evaluate how efficient they are is the n-half metric, which is basically the length of the loop which is required in order to achieve at least half of the maximum speed of the pipeline. Okay? We will see in a minute how this works. We have a certain number of operations per loop, and the total loop takes basically the number of loop iterations times discounter operations. So the performance, the speed of our loop is basically the total number of operations divided by the time it takes, right? We can now replace the total number of operations by this formula. Actually, let me mark it over here. Oh no, I can't mark it over here, so I'll show it here. Okay? And the total time, well, how many cycles do we need to execute the loop? The first iteration of the loop will take as many cycles as the pipeline has stages, which is m. And the main idea behind pipelining is that afterwards, on every cycle, you have one result item coming out. So all other n-1 iterations of your loop will take one cycle. So we have all in all m plus n-1 clock cycles, okay, which it takes to execute this, assuming there are no hazards, stalls, whatever. And each clock cycle takes tc seconds. You can slightly rewrite that to get and to get this form of for the formula for the speed of your loop. And now what you really want to do is, okay, let's assume our loop is infinitely long. That's when we get the maximum theoretical speed for that according pipeline. Okay? So if you let n go towards infinite, what happens is this part goes to 0, or is 0, and you will end up basically with your maximum speed for that pipeline, for this loop, being the number of operations per cycle divided by the clock cycle time. Okay? So that's good. Let's try to define now what n half is. And what we can really do now is, having the maximum speed of your pipeline, we really want to know how long does n have to be in order to achieve half of that. Okay? So n half is in reality a half of f max, which we determined on the previous slide. And what we can do now is we can basically use this formula as well as this formula in order to determine that. So we have on one side, we know that the maximum speed is number of operations divided by clock cycle time. So half of that speed is basically the same formula divided by 2. On the other side, if we want to know the number of iterations, well, you basically take the previous formula which we used to derive this formula over here, and you replace the lower letter n by the number of cycles or number of loop iterations which we are looking for, and suddenly you have here a formula where you can derive n 1/2 from. Okay? And if you're doing that, you see that n 1/2 is equals to n minus 1. So if your pipeline is 24 stages, your loop should have at least 23 iterations in order to achieve half of the maximum theoretical speed of that pipeline. So is the general idea clear? I mean, the mathematics is not difficult. You can look at it at home. But basically, we evaluate the maximum speed or the maximum performance of a pipeline for a particular operation or for a particular loop. And in order to determine how many loop iterations do we need in order to achieve half of that performance, well, you basically use the same formulas in order to derive n 1/2. You can further, you can actually further extend that concept to have not just n 1/2, but to have any n alpha, right? You are doing exactly the same thing, with alpha being between 0 and 1. So you have on one side alpha times number of operations divided by the clock cycle time, and here you have n alpha in the denominator. And if you're transforming that formula such that you have an expression for n alpha, you end up with something like, it's not a precise formula, m times 1 over alpha minus 1. What this basically means is, if you look at, let's say, alpha being 0.75, that the number of loop iterations in order to achieve 75% of the maximum speed is now suddenly 3 times the number of stages. Okay? So, more generally, the closer you would like to get to the maximum performance of your pipeline, the longer your loop has to be. And this is actually, so this is generally true, but as you can see here, in this formula, the number of stages of your pipeline is the only relevant factor. So making your pipeline very deep with a large number of stages means you need a larger number of operations and instructions in order to achieve its full performance, or close to its full performance. Yeah? I will add these slides to today's lecture. Usually I did do this at the beginning of the pipelining section. I wonder why I didn't do that this time, but, well. Questions to that part? Okay. Let's come back to computer architecture. So we discussed now superscalar architecture as an architecture which can issue multiple instructions per clock cycle. The number of instructions which we can issue is flexible, is not fixed. Yeah. And while issuing the instructions, we basically check for dependencies and hazards between the instructions as well as between instructions in the issue packet as well as between instructions which are going to be issued and already issued instructions. So all of this adds once again more to the complexity on the hardware level. So the alternative approach is really have the compiler look into the occurring things and let the compiler decide which of those instructions can be executed at the same time. And as I mentioned, that's basically what a very long instruction word processor does. It typically has a single large instruction nowadays. Okay, so, well, there's just one processor out there, which is the Itanium processor. He really has not n small instructions which are being issued, but it generates a single large instruction which in reality contains multiple instructions. Yeah. We will see, I don't know whether next time or in 2 weeks, a couple of slides on the Intel Itanium processor. I think I don't have them right now here, just to give you an example on how a very long instruction word processor works and what the drawback and advantages are. Yeah, so basically, the very general concept or the general idea is that you try to reduce the hardware complexity, you try to reduce, therefore, the power consumption, and you shift the burden towards the compiler. So I don't know how many of you remember, but when Intel established together with HP the Itanium line, they started to invest at the same time into their compiler group. They significantly extended it. They delivered compiler for the Itanium, because clearly if you just port your regular GCC onto such a compiler, you will not see any benefit. If the compiler doesn't know what he has to look for in the according, how to mark parallelism between instructions, etc. Questions? One last time, questions to the quiz? No? Okay, then see you on Monday, 5 to 1 here. Yeah. Yeah. If you have any questions, contact me by email or come to my office, yeah? Thanks. Mm-hmm. 1 second. Let me try to stop the recording.